Hello and welcome. And today, let's see another exam objective of using automated ML to create the optimal models. Now, before we get into the details of this exam objective, let's first see what is AutoML. And for that, let me revisit the typical machine learning workflow. So we know that every machine learning experiment will go through these stages of data ingestion, data processing, then training and building the model before final deployment. And here I have simply created one such experiment for the credit card defaults dataset. So in a nutshell, we select the features or columns, clean it, normalize the data, and then apply different algorithms on it. Now, as you can see, we can apply different algorithms on the same data. We have even applied this tune model hyperparameters for each of them. We have then scored them and then compared them using the evaluate model. Now imagine, just for argument's sake, we want to test 15 different algorithms. Then we may have to pull in all of those and then compare their results manually. Now, this example slide that you see here is for the designer or Classic Studio. Imagine if the same thing needs to be done using Python and libraries such as scikit-learn. Then it will be a huge task in itself. And if I may present this process slightly differently, then during data processing, for each of these features, we would be asking questions related to the feature selection, dealing with missing values, and so on. We most certainly have to code them as well. Then during model building and selection step, we won't know which algorithm to select and which one will be the best. And because of that, we may want to try different algorithms, and each of these algorithms will have their own set of parameters. And we may even need to tune them separately. And then finally, we compare the goal or the primary metric, such as accuracy, and then select the best model. Now, that is one big manual and very time-consuming process. And that is where the Azure AutoML helps us. Now, Azure ML is a product that has been developed after years of research by Microsoft, and it makes our life very, very easy. And all you need to do is bring in your dataset, the same way we used it for other experiments. Then the second step is to define our goal, or the primary metric for the type of problem that we are dealing with, such as accuracy, AUC score, or precision, and so on. So this is basically for evaluating different models and to create ranking based on this primary or the goal metric. Then apart from these two, we can also specify the constraints, such as the maximum time or iterations for which it should run. We can even block any particular algorithm that we do not want to train. So basically, we can chop and choose various algorithms. And once we have done that and submit this AutoML experiment, it generates different runs or iterations using various combinations of features, different algorithms, different combinations of their parameters, and then starts generating various metrics of these runs. And finally, based on this goal or the primary metric that we defined, it automatically provides us the ranking of these models. And this entire process is pretty much automated. We simply need to worry about bringing in the data and the configuration part for time constraints, etc. Rest everything is taken care of, and we are presented with the best model at the end of the process. And finally, at the click of a button, we can simply deploy that model. Isn't it amazing? And this can surely bring in a very revolutionary change in the way we build and deploy the machine learning models. At least that is true for the routine or datasets with simple to medium complexity. For them, this is simply amazing. So let's go ahead and see it in action using Studio as well as Azure ML SDK. As always, thanks for joining me here. Hello and welcome back to the studio. Now, before we start this new automated ML, we need to have a dataset. So make sure you have the defaults dataset uploaded to the workspace. Then we also need a compute cluster to run the AutoML experiment. So make sure you have a compute cluster created over here. I have this my cluster 001 already provisioned. Now, to start the automated ML run, we simply need to click on this Start Now button of automated ML. For now, I don't have any AutoML runs, so let's create one by clicking on this plus new automated ML run. Now here, it has these three main steps of selecting the dataset, then configuring the run, and finally selecting the task and settings. So in this Select Dataset tab, you can either create one if you don't have by clicking on this Create Dataset button, or you can choose from any existing one. I have already uploaded the default dataset, so I'm going to select that and click on Next. Then as part of configuring the run, we need to provide an experiment name. So I'm going to create a new here as I don't have any, and let's call this one as AutoML EXP001. Then select the target column or the predicted column. So select the default next month column. Select the compute cluster of my cluster 001 over here, or whatever name that you have provided. Then you can create it from here also in case you don't have it. But again, it's an unnecessary interruption to our learning flow. So it is always better to create it and then start this particular configuration. So let's now click on Next. And now we need to select the task type. And as you can see, it has already selected this classification type. But we can also choose from regression or time series forecasting if that is the problem we are trying to solve. Okay? So these are the only three options that the AutoML currently has. Then scroll down a bit, and here we have these additional configuration settings and the featureization settings. I don't know why they are mentioned as a sub-part of this final step, because they are a very important part of this entire process, and I think it would have been good if they were a separate step. Anyway, so for now, let me click on this link of View Additional Configuration Settings. And here first you will see this drop-down of primary metric, and you can choose from accuracy, AUC, precision, this normalized recall, and others. For now, I'm going to keep it to the default of accuracy for this experiment, and then let this checkbox of explain-based model be checked. And in simple words, this simply means it will show us various feature importances for that particular model. Then moving to the next, here if we do not use a particular algorithm, we can do that as well. So if you click on it, it shows this list of algorithms that are available, and if you want, you can block one or more of these. I mean, that's only if we have some idea beforehand that a particular algorithm cannot be used for that dataset. All right, and then simply expand the exit criteria, and here you will see the constraints of training time in hours. So the default is 3 hours. I think that is more than enough, but if you want to quickly see the results or save some cost, you can choose the minimum, that is 0.25, which means it will run for just 15 minutes. But this is actually the model training time. It has nothing to do with setting up the environment and other time. Then depending upon the metric threshold value here, we can make the AutoML run stop. So that basically means if we provide an accuracy of let's say 0.7 as the threshold, and one of the model reaches that threshold, then the AutoML run will stop and no further iterations are done. So whichever model achieves that threshold first becomes our best model. So let me just remove this 0.7. Then under validation, this is simply for cross-validation or creating different training and test dataset. So this option of train validation split is nothing but what we commonly know as train test split. The test dataset is also known as the validation data, as it validates what we have trained or the training that we have provided to the algorithm. So select that, and then in this text box, provide 30 as the percentage of data going to test or the validation dataset. Great, and we are now almost done on this. So then under this concurrency, we have max concurrent iterations, and here we can specify how many models or runs can happen in parallel or concurrently. Now remember, this is happening on a compute cluster, and every cluster has some maximum number of nodes. So this value cannot be more than the maximum number of nodes of our compute cluster. So I'm going to keep it to 2 because that is the maximum node for my cluster. And then click on save. Great. And next, let's click on view featureization link. And here it will simply show you a list of all the features. Again, we can decide to either select or deselect them. For now, I'm simply going to deselect this ID column. Then here you can tell the AutoML what type of feature is this. So whether it is numeric, datetime, categorical, or others. For now, I'm simply going to leave it to auto. Then even for this impute with section, which basically means how the missing values will be replaced. And there I'm going to leave it as auto for all of them. But as you can see, if you want, you can always specify that as a mean, mode, median, or a constant value. So for now, leave it to auto. All right. And let me now click on save. And we are now set to click on this finish button. And it will then submit the AutoML run. So go ahead and hit finish, and let's see what happens next. It will show you this box of validating, creating a new run, and then will redirect us to the run 1 for this AutoML run. For now, I have just provisioned this cluster, so the AzureML is going to set up the environment, etc. on those nodes. And then we also specified the runtime limit as 15 minutes. So let me end this lecture here for now, and then come back once it has finished running it. So if you have been doing it along with me, take a break, have a cup of coffee or tea, but make sure you come back after 15-20 minutes. That way you can view the results as soon as it finishes, as well as you can delete the compute cluster as well. And I'm sure you don't want to keep the compute cluster up and running for a long time. So see you soon on the other side, and good luck if you have submitted your AutoML. I'm pretty sure it should go fine. Thanks for watching. Welcome back. The run has finally finished for me, and it took little over half an hour to finish everything. And if you have also achieved this, congratulations first. And then let's now go through the details of it. So let me click on this experiment of AutoML EXP001. So as usual, we have this summary of the runs, but we are interested in the details of it. So click on this run 1, which is the first or the master run of all the other child runs. And here you will start seeing various details as before. But now we also see this best model summary that has the algorithm name with an accuracy of 0.768. You will also see the run summary for task type as classification, primary metric, and the experiment name. And then let's click on this data guardrails tab. It is some fancy name, but has a very simple explanation. So the data guardrails are run whenever we keep the featureization in auto mode, which is what we did. If you remember when we saw that big list of all the features and the auto was on for all the features. So here it has these 3 basic checks of class balancing detection. So it tried to find out if one of the predicted classes has a very low number of occurrences or not. So if it is dominated by just the yes or just the no's, then we call it an imbalanced dataset. And that was not the case for us, so it passed the check. Next, it performed the missing value replacement or imputation. And if you click on this view additional details, and indeed it had some missing values here, which it has taken care of. Then it also checked for high cardinality features. Again, a very fancy name, but it simply means the columns with huge number of unique values. So something like the ID or email or phone number, and these are considered as high cardinality features because they are unique for almost all the records. Then, because we didn't include the ID column, it has passed that check as well. Next, let's see different models that has been created for us. And there you go. We have roughly around 15 models created over here, and as you can see, they have been sorted based on the primary metric of accuracy. We even have the explanation for the best model. Now, just in case you get frightened by all these models, remember, the exam may not test your knowledge on these models and these algorithms, but we are required to know how the best model has been selected. Okay? Great. Now moving on to this sampling, which mentions 100%, and that simply means the entire training data was used for training the model. Then we have this run number and other basic details. I'm sure they are self-explanatory. So let me right-click on this run 18 and open it in the new tab. So here we have the details of it and a summary of various metrics over here. Now, if you want to deploy this model, you can simply click on this button called Deploy. And then on this screen, simply provide the details required and you will be able to deploy it. But before this, let's see the metrics. So click on the Metrics tab to view the detailed metrics. And here you can see all these different metrics and various charts, including the ROC curve. And these metrics can be very overwhelming. So let me keep the accuracy and deselect the accuracy table, AUC macro, AUC micro, as well as the weighted AUC. Then come down a bit and select the confusion matrix, which gives the true feeling of what exactly happened with these predictions. And give it some time if it does not load the confusion matrix as a chart over here. It shouldn't take long. Great. Now this model has the highest accuracy. We know that. And is supposed to be the best model for us. But have a look at this confusion matrix. It actually predicted everything as false, except this one record. So basically, it means nobody is going to default. I hope you are with me. And what I mean is, it has predicted no for the default next month column. Now, even though this model has highest accuracy, it is of no practical usage. And this is called as null accuracy, where the model starts predicting just one class. And we do not want to put a model in production which predicts that nobody is going to default. So what should we do? Well, let's go back to the master run of run 1 and scroll down a bit. And let's see the worst model that we have, which is this run 10 with just 62% accuracy. Let's open that in the new tab. Again, go to the metrics. And here you will see that the confusion matrix has predictions for true, which means some are predicted to default the credit card payment. So it has correctly predicted that 46 out of the 112 actual defaults will default in the next month's payment. But it has incorrectly predicted that these 115 customers may default, even though they may not. And that is why the accuracy is so low for this model. Now, even though this model has lesser accuracy than the best model, this is much more practical. Maybe the bank wants to send a reminder call or SMS or an email reminding the customer that his payment is due. That way, we can avoid the default by a few more customers. And even though there are these 115 customers who may not default, the cost of sending those messages, emails, or calls will be substantially lower compared to the gains. So you should always look at these options before we can decide on the best model. So what I'm going to do in the next lecture is let's create the AutoML run using the Azure ML SDK. And then let's explore a few more features of the automated machine learning. And trust me, that is going to make our life much more flexible with the Python code. Great. So see you soon in the next one, and thanks for joining me here. Hello and welcome. And in this lecture, I just want to touch base once again on recall and then explain the norm macro recall that we talked about earlier. So as you know, recall is nothing but the ratio of true positives divided by total number of positives. Now, what happens is majority of the time, we are dealing with binary or two-class classification. In that case, we are dealing with only two outcomes. And we can call one of the outcomes as positive and another as negative. But when we have more than one outcome, we can only divide them into multiple classes. So if we treat this two-class classification as a multi-class, then this formula of recall does not hold true. So in that case, we need to take the essence of it. And what I mean by that is we need to tweak the formula. So now, instead of positive and negative, what we will say is correct predictions of that class divided by the total actual observations of that particular class. I know the words can be misleading, so let's calculate it. So for class 2, we have these 46 observations predicted correctly, whereas the actual class 2 observations are 46 plus 66. So when we solve it, the recall for class 2 will be 0.4107. And similarly, the recall for class 1 will be correctly predicted class 1, which is 253 divided by 253 plus 115. So that will be 0.6875. I hope you are clear until this point. Then the macro recall is nothing but the average of these two recalls. So when we impute these values and solve it, you will get this value of 0.5491. Great. And that is how all the macro metrics are calculated. And I'm sure now they are not alien to you. And in case of Azure ML, it does not distinguish between two-class or multi-class classification. Everything is calculated as multi-class, and that's why the metrics are in this fashion. And if you remember, the value for macro recall was exactly same for the run 10 of the previous run. But in cases where one of the class dominates heavily, this macro recall may not give correct results, or won't be the practical results if I may say. For that, we need the normalized macro recall. So in case of normalized recall, the formula changes to this one. And here we subtract this constant of r from the macro recall and then divide it by 1 minus r. And r here is nothing but the inverse of the number of classes. So in case of a two-class classification, C is 2, and that's why r becomes 0.5. And when we impute these values in this formula, we get the norm macro recall as 0.0982. If you want, you can go back to the run 10 or any other run and then calculate it based on these formulas that we have seen here. And I'm pretty sure you will get the same result. The normalized recall actually provides a much better indicator of the overall correct predictions compared to just one class recall or even compared to the macro recall. And I'm sure you must have guessed that it will be 0 when we cannot predict one of the classes correctly. And when we predict everything correctly, it will be 1. So higher the better. Alright, and now let's go ahead and see how to use the automated machine learning using SDK in the next lecture. As always, thank you so much for watching. Welcome back, and now in this lecture we are going to configure and run the AutoML experiment. I have already listed down the steps required to do that. The first 3 of accessing the workspace, getting the input data, as well as creating the compute clusters are pretty easy, and we have done them numerous times. Then we simply configure the AutoML run, and you will see that it is also pretty simple and similar to the configuration we did in the visual interface of Studio. And finally, we create and submit an experiment. Alright, so as you can see, I have imported this class, accessed the workspace using the config file, and also got the input dataset. And this time, I'm simply printing these messages so that when we run the program, we know exactly where it is. And because we knew how to create the compute cluster, I have gone ahead and coded that as well. But this time, it is slightly different. This code simply enhances what we have been doing earlier. Before this, we simply went ahead and created a new cluster. But here, after initializing the cluster name and importing this class, I have this if-else block. So first, I'm checking whether the compute target with this cluster name exists in this workspace or not. So this attribute of compute_targets of the workspace object returns a dictionary. And this dictionary is of all the compute targets within that workspace. And if it is not found in that dictionary, then we simply configure it and use the create method to create it. And if it is found, we simply access it in this else block and then assign it to this variable of cluster. I hope this is clear. And this kind of a block helps if you are doing multiple experiments in one sitting and do not want to recreate it or execute the code in parts. Alright, great. So next, we need to import a class for AutoML configuration. And for that, let me type from azureml.train.automl import the class of AutoML config. And this is case sensitive with A, ML, and C capital, as you can see here. Then let me just add a print statement as print and within parentheses within quotes, creating the AutoML configuration. Great. Then let's create the object of this class as AutoML_config equals to, and this class of AutoML config followed by 2 parentheses. And now, if you remember the flow from the visual interface, we need to provide the type of machine learning task as either classification, regression, or time series forecasting. So here, that will be a parameter called task equals to, and in quotes, in all small case, classification followed by a comma. So this will tell the AutoML that we are doing a classification type of task. And in the next line, let's also provide the compute target as compute_target equals to, and this object of cluster. All right, and another comma. Now we can do AutoML on local machine as well, but very few features are available for local runs. And that's why it is always better to run it on a compute cluster attached to the workspace. Then in the next line, let's now provide the input dataset as training_data equals to input_ds, where we have stored the dataset. And remember, this has to be an AzureML dataset, which is what we have here. So the entire input dataset is considered here as the training data. And if we want to create a validation or the test data out of it, then we need to provide another parameter called validation_size equals to, and a value between 0 and 1. So as we did in case of visual interface, let me provide 0.3 for 30%. This is pretty self-explanatory. Then we also need to provide the predicted column name. So in the next line, provide the parameter of label_column_name equals to, and within quotes, the column name of default next month with the first letter capital for all the words. Great. And you must have noticed here that we can provide these parameters in any order compared to the visual interface. And we can even reuse these runs because we don't have to type it again and again. And that's because these are simple keyword parameters. And it makes it very easy if we want to rerun or we want to create a new run out of this particular template. Okay. Then next, let's also provide the primary metric as primary_metric equals to, and within quotes, now here, instead of accuracy, as we did earlier, let me provide what is known as norm_macro_recall in quotes. I hope you remember what is recall. So this is simply the normalized form of the recall. I will explain that once we come across that in metrics. For now, let's go ahead and provide another parameter of number of iterations as iterations equals to, and let's say 10 for now. Okay, followed by a comma. And in the next line, the maximum concurrent iterations as max_concurrent_iterations equals to 2. Okay, And then let's also put a constraint of time as experiment underscore timeout underscore hours equals to, and then 0.25, which is same as before, which means 15 minutes. And finally, let's provide the featureization setting as featureization equals to, and in quotes, auto. And for the non-American students, this has to be with a Z or a Z. Great. That's it. And for now, the bare minimum that we need is in place. And make sure all the commas and quotes are also in place. Great. And now let's create an experiment and submit this AutoML run. So let's import the experiment class as from AzureML dot core dot experiment import experiment class. Okay. And then create a new one or a new object out of this experiment as new underscore exp equals to the class of experiment, and within parentheses the workspace as ws object, comma, and within quotes let's give a name as AzureML -SDK -exp -001. Great. And let me also print it as print within quotes and within brackets submitting the experiment. All right. And finally, to submit a run, let's create a new run object as new underscore run equals to this experiment object of new underscore exp dot the method of submit. And then within parentheses, we now need to provide the AutoML configuration object, which is this AutoML underscore config. Great. We are almost done. And all we want is for this run to wait while the script is running. So that will be new underscore run dot wait underscore for underscore completion. And within the parentheses, show underscore output equals to true. Great. And for now, that is all that is required for the AutoML experiment. And as you can see, compared to the training experiment and the pipeline runs, where we had to create those scripts and then run them in a job script, here we just need to configure it and then submit it. And with that, we are now ready to run this AutoML experiment. So let me select these lines and hit Ctrl plus Enter to execute it. And very soon, it will start printing these messages of accessing the workspace, accessing the dataset, as well as the compute cluster. And because it does not exist, it will create a new compute cluster. So as usual, give it some time, and it should be done in around 25 to 30 minutes. So please allow me to end this lecture here, and I will come back once it has finished running it. So see you soon on the other side, and thanks for watching. Welcome back. And now as this AutoML experiment runs and goes through all these steps, it starts accessing the workspace, dataset, create a cluster, and finally submits the run. And you will also see this message of running on remote. And let that happen for some time. And then after 5-6 minutes or so, you will see these messages of featureization and model selection flashing on your screen. And similar to what we saw during the visual interface, you will see the runs for data guardrails displaying these messages over here. Then it will finally start building the models and display the results of each of them on the console over here. And because we specified 10 iterations, it should be done pretty quickly once it starts these model building steps. And very soon you will see the status as completed on the console. So congratulations first, and now let me show you how to retrieve the best model as well as print these metrics using Python and AzureML SDK. It's pretty easy, and all you need to do is use this object of new underscore run dot and a method called get underscore best underscore child with 2 parentheses. Select and run this line, and it may take few seconds, and very soon you will see the best run printed on the console. And there you go, we have this run ID ending with f_4, which is our best child run. If you want, you can assign this to another variable and then store it or use it if required. Now remember, this best child run is considering the primary metric that we have specified. And we specified the norm macro recall as the primary metric. But if you want to get the best child based on some other metric, you can always do that by specifying inside these parentheses a parameter called metric equals to, and let's specify accuracy in quotes. Select and execute this line. And this time it may take slightly longer because it is not straightforward. It needs to extract the accuracy for all the runs first, and then compare them and then provide us the best run. So give it maybe 20 to 30 seconds and it should be done. It is done for me, and as you can see, it has retrieved this best model with the run ID ending with F7. So as I said, it is not cast in stone that we have to use the best model from the primary metric. If you want to use some other metric, you can always do that. But then the question is how to get those metrics for all the runs. Well, it is pretty simple. So here we used this get best child method, and similar to that, we also have a method called get underscore children for getting all the child runs. And for that, let me run a for loop as for run in new underscore run dot get underscore children with 2 parentheses. So this method will fetch all the runs, and we then extract one run in one loop in this object of run. And then inside this for loop, let me first print a blank as print and just the quotes in parentheses. And then let's print the run ID first as print, and within parentheses, let me first give the title of run ID in quotes, then a comma, and then the attribute of this run object called ID. So that will be run.id. All right. Then to get the different metrics from this run object, we need to use a method called get_metrics, which will fetch all the metrics for this child run. So let me print it as print and within parenthesis run dot get_metrics, and inside another parenthesis we can specify the metrics name. So let's get the accuracy first. So specify accuracy in quotes. Great. And then let's also get the primary metric for this run, which is the norm macro recall. So let me just copy and paste this line, and then change the accuracy to norm_macro_recall. Great. Everything looks fine. So let me select and execute this for loop. And very soon you will start seeing various run IDs starting from the F9, and it will print their accuracy and the norm macro recall. And here we have only chosen the 2, and that's why I could just print 2 statements and it was done. But if you remember, it gives us 15 to 20 different types of metrics. And if you want to get all those metrics, you can simply put this run.get_metrics in a for loop and then print all of them. So it will be just another loop inside this for loop, and you can simply code it as for metrics in run.getMetrics and then start printing inside that. Great. And if you want to view it in the studio, it will be exactly similar to the earlier AutoML run that we did. And I'm sure you now know how to run the AutoML experiment using the studio interface as well as the Azure ML SDK. We also saw how to configure these runs, how to provide the data to these runs, as well as how to pre-process them and the featureization options. Then we also retrieved the best model as well as the metrics for all the runs. Great. And that brings us to the end of this lecture on Azure AutoML using SDK. And before we end this lecture, if you do not want to use the compute cluster, I suggest delete it by going to the workspace or delete the entire workspace from the Azure portal. Alright? So see you soon in the next one, and thank you so much for joining me here. Hello and welcome. And today let's see another important exam objective of using the hyperdrive to tune the hyperparameters. Now, if you remember during the tune model hyperparameter lecture in the section of Classic Studio, we saw that all of these algorithms have these parameters. We can then tune these parameters in their best possible combination to get the best results. We can also determine various primary metrics for that. Now, just in case you have tried the tune model module in Designer also, you will realize that there is no difference whatsoever compared to the Classic Studio. But when it comes to using the hyperdrive in the Azure ML SDK, the process slightly changes. And these exam objectives are also in line with that process. Right now, even though these may not make much sense, it will be absolutely clear as we go through them in the subsequent lectures. So some super exciting stuff is coming up in this section. As always, thanks for watching. Value after the decimal digits. And in such cases, if we need to provide these values, we cannot do that as a simple range of values. We may want to select it from some sort of distribution. We may select the values from either a uniform distribution between the low and high values. So it may pick up anything at random between these two values. Then we can also pick up the log uniform value for the parameter. Now remember, this log uniform value is nothing but the exponential value of the uniform distribution value. So first it picks up the value from this uniform distribution and then takes the exponent of it to get the log uniform value. And in the same manner, we can also define the parameter search space using the normal distribution of the parameter. And here we simply specify the mean and the standard deviation of the proposed normal distribution for the parameter. So in this case, it will pick up the values or define the search space based on this normal distribution curve. Alright? And then again, the log normal here is nothing but the exponent of the value taken from this normally distributed curve. Great. I hope that makes it clear about what we mean by the parameter search space and how we can define it based on whether the parameter is either discrete or continuous. In the next lecture, let's see what are different sampling methods and how to select them. Thanks for watching. Welcome back, and now let's see the sampling methods that are available in the hyperdrive. So we have 3 sampling methods of random, grid, and Bayesian sampling available for hyperdrive. If you remember, we had a random, grid, and a random sweep for Classic Studio as well as the Designer when we use the tune model hyperparameter module. So there is a slight deviation from that when we use hyperdrive. Now during that lecture, we also saw what is our grid, how the random sampling as well as the grid sampling works. And here let's see the comparison of these 3 sampling methods as far as hyperdrive is concerned. So the first thing is the random and the Bayesian sampling methods support both the discrete as well as the continuous hyperparameters, whereas grid only supports the discrete hyperparameters. So you may want to choose and apply these sampling methods based on the type of hyperparameter. So if you are only dealing with the discrete type of hyperparameters, you can use any of these 3. But if you have a combination of discrete and continuous, the options are only 2. Then the second difference is how they are applied. So random as well as grid sampling will run the experiment for different combinations and then provide the best one to us. It does not bother how the previous run went, or does not take into account the information from the previous runs. So you can say that all the runs are executed in kind of some sort of isolation. But that's where the Bayesian sampling scores a point. It selects the next set of hyperparameter based on the information from the previous run. So it checks whether the primary metric is improving after every run, and depending upon that, it will choose the next set of parameters. And for that, it applies what is known as the Bayesian optimization. At this stage, it is good enough to know what Bayesian sampling is used and how it is different than the other two. It's actually slightly more advanced topic, and detailed explanation may not be required as part of this exam. Alright, and then the last point is about the early termination. Now, many times we need to terminate a particular run a bit early than the required. And the random and grid sampling supports the early termination, whereas the Bayesian sampling does not support early termination. And that is precisely what we are going to learn in the next lecture. It's a very interesting topic and could be a bit tricky to understand, but let me give my best to make it simple for you. So see you soon in the next one, and thank you so much for watching. Hello and welcome to this new lecture on defining the early termination options for the hyperdrive. So before we see what is early termination policy, I hope you remember this diagram of gradient descent, which we saw during the regression using stochastic gradient descent lecture. And I also showed you one example of how the cost goes down up to a particular point before it starts rising. We then used the learning rate to go down this path and try to find the minima in case of the cost function. But before we take a first step, we need to read all the records or maybe a portion of it, and then predict the y, then calculate the loss or the cost, and then only we will take the next step, which could be somewhere over here. And we keep on doing that until we get to the minimum. And these steps, irrespective of whether we start from here or here, are called as the epoch or epo or iteration or intervals. That also means the algorithms which use this kind of training mechanism are computationally heavy or expensive. And you may wonder, why am I telling you this in this lecture of early termination? Well, think about it. There could be an algorithm that we are going to train, and we give two parameters of learning rate and number of epochs or iterations to it. Now, typically, for a larger learning rate, even though we may reach the bottom very fast, but there is a danger of oscillating around this minima, because we may take a larger step and will always overstep this bottom. And let's say, hypothetically, for this algorithm and a learning rate of 0.2, we reach this stage of oscillations after 20 iterations. But we have specified these values from 50 until 1000 for this hyperparameter. And that can lead to lots of wastage of computing power as well as much more time. And that we could have probably saved if we stopped after 20 or maybe 25 iterations once we discover that there is actually no gain. Well, that's where the early termination or stopping policy comes into the picture. So we have these four policies of bandit, median, stopping, truncation selection, and of course no termination policy. I'm pretty sure you know what no termination policy means, so let's see the other three and start with the bandit policy. Bandit policy has these four parameters. Out of that, we can either specify the slack factor or slack amount, but not both at the same time. So let's see the bandit policy with slack amount first. So if you are going to implement it, you need to import this class called bandit policy from the azureml.train.hyperdrive, and then create the policy using these three parameters. Now the delay in evaluation parameter simply means delay applying the policy for those many intervals. So in this case, it will apply the policy after 10 intervals. Then evaluation interval of 1 means apply it on every interval after the 10th interval. And if you specify 2, then it will apply on alternate intervals, and so on for 3, 4, or 5. Then this slack amount is a bit tricky. So for the 11th and all the future intervals, what it will do is, it will check the primary metric of the best run till that point, and then subtract the slack amount from the metric of the best run. And if the primary metric for the 11th run or any other subsequent run is less than this value, then it will terminate it. So let's say that during the first 10 intervals, if the fifth one, it actually does not matter, but let's say for argument's sake, the fifth one returns the best accuracy of 0.9. Then if any interval or epo that returns the accuracy less than 0.8, then it will be terminated or stopped. I hope that is clear. Now, when we apply the slack factor, everything else remains the same, just that the calculations are a bit different. Now here we add the current metric. Now here we add the current primary metric multiplied by the slack factor to the current primary metric. So we are basically multiplying the current primary metric by 1 plus the slack factor. And if this result is still less than the primary metric of the previous best interval, I hope you are still with me. This result, if it is less than the primary metric of any of the previous best interval, we terminate the training run or this current run. I hope that is clear. It's not that difficult once you understood the previous one of slack amount, just the calculations are a bit different. Then comes the median stopping policy. And as you can see, it has just two parameters of evaluation interval and the delay in evaluation or delay evaluation, because the third one is part of the class itself, which is median. So what this policy does is, it calculates the running average of all the previous runs. So for the first one, it will be same as this accuracy. Then let's say the second one reports the accuracy of 0.86. So now the running average will be sum of these two divided by the number of intervals, which is just 2. And then it goes on until this delay evaluation parameter or even for subsequent runs. But after the delay evaluation interval, so let's say for the 6th or any subsequent run, it checks if the primary metric or the accuracy in this case is less than the median of all the previous running averages. And if at all it is lesser, then it stops or terminates that particular run. Alright? And finally, we have the truncation selection policy. So in this case, after the delayed evaluation of the policy, we simply expunge or we do not select the bottommost percentage of runs as specified by this parameter of truncation percentage. So in this case, after the 10th interval, we will expunge these two or the 20% of the 10 intervals or the epochs that gave the least accuracy of 0.85. And it will keep on doing that after every evaluation interval, which means it will expunge the 20% of the bottommost ones after every interval. Alright? I hope I could make it simple and easy to understand, because if you read any blog or even the description from the official Microsoft link, it could be a bit confusing. And remember, we cannot or need not apply the termination policies on each and every algorithm. Only those algorithms using iterations can have this early termination policy, such as the classifiers and the regression algorithms based on the SGD or the stochastic gradient descent or XGBoost or most of the deep learning algorithms. Great. And now let's go ahead and implement the hyperdrive in Python. I hope you are enjoying learning these concepts in the simplest possible manner. Thanks for watching. Hello and welcome. And let's now configure the Azure ML hyperdrive using Python. And as you can see, I have already coded some of the lines, and by now we have done them numerous times. So as usual, we are importing the classes, accessing the workspace, and also getting the defaults dataset. Then I'm creating the custom environment as before, but this time I have done some small changes here. I have included the Conda package of pip and the pip package of Azure ML defaults. It can work even without it, and if you remember, there used to be a message that we have not specified it. So that's the only minor change here. Then again, this compute cluster step is the same as before, which is we check it, create it, or use the existing one. Great. Then here we are going to run this hyperdrive experiment as a script. And what I mean by that is instead of a pipeline run, we are going to run our training script similar to the way we ran the entire script. And because of that, I have specified this script run config. Then you have the same things such as the source directory, script name, environment, as well as the compute target. I have also added this one extra parameter where we are passing the input dataset as the named input with the key as raw_data. You can either pass it here or you can even access it from the script. Both the ways are perfectly okay. Alright? I just wanted to show you that we can use this arguments parameter inside the script run config as well. Next, let's create the object required for hyperparameters. And here I'm going to use the grid sampling method. So for that, we need to import another class called grid parameter sampling. So that will be from azureml.train.hyperdrive import grid parameter sampling with G, P, and S as capital. Okay, and let's now create an object of this class, and let me call it as hyper_params equals to, and let me copy and paste this class of grid parameter sampling. It's too big to type again and again. And this is followed by two parentheses. Now here we need to provide the parameters of the algorithm that we plan to use in our script. And here I have planned to use the random forest algorithm from the scikit-learn library. So as you can see, it requires multiple parameters. But for this experiment, let's just use the two of the number of estimators or the number of trees in the forest and the minimum samples per leaf node. So let's go back to our script and code for these. So this class needs the parameters in the form of dictionary. So first the two curly brackets for dictionary and the parameter will go as the key. So that will be in quotes n_estimators colon and the list of various parameter values. But there is another function called choice using which we need to provide this list of parameter values, particularly for the hyperdrive. So let me type choice and in brackets, let's say we provide 10, 20, 50, 100 as the four different options. And I'm sure it will give us this error that we have not defined choice. So let's just import it from the same package of hyperdrive. So a comma after this grid sampling class followed by choice. Great. And let's now provide the second key for minimum samples in a leaf. And that will be in quotes after this first parameter of n estimators, min_samples_leaf colon and choice again. And then within the parentheses, let's say 1, 2, 5. So basically total 4 into 3 as 12 different options are possible for this combination of parameters. What that basically means is our training script will be called 12 times for every possible combination. And every time it is called, we need to pass these parameter keys to the script. So how should we pass it? Well, we have done it multiple times in the past few lectures. Great, that's right, as an argument. So to make it an argument, we simply add 2 dashes right before this n_estimators as well as before the min samples leaf. Alright, and that completes the definition of the hyperparameters. Make sure all the different brackets and commas are closed properly. And this is just the definition of the grid sampling. Next, we need to configure the hyperdrive class, which we will then submit to the experiment. For that, let's create an object as hyper_config equals to, and the class for creating the hyperdrive configuration is known as hyperdrive config with H, D, and C capital, followed by 2 parentheses. And as always, it is going to give us this error. So let's import it as from AzureML dot train dot hyperdrive, everything in small case, import hyperdrive config, and as I said, HDNC as capital. Great. And first of all, let me select and run this import statement so that we have the class available in the Variable Explorer. And then go to the Variable Explorer and open the hyperdrive config class. Let me maximize it and also adjust this frame. And now, as you can see, we need to provide various information such as the estimator, sampling details, early termination policy, the primary metric using which we are going to determine the best combination of hyperparameters. And then what's the goal for the primary metric? So whether we want the maximum value for the metric or the minimum. Majority of the time, you will use the accuracy, AUC, or one such metric, and that's why you will see this option as maximize. And then we need to provide the maximum number of runs as well as the maximum number of concurrent runs. So it is pretty much similar to any other configuration that we have seen. So let me just scroll down a bit and also show you this line that says we need to provide only one of these three options. So we can either provide an estimator or a pipeline object or the run configuration object. For our case, we will provide the script run config object that we have created earlier as the run configuration. Great. So let me close this. And now the first parameter I'm going to specify is the run configuration. So that will be run underscore config equals to the script underscore config, where we have specified the environment, cluster, as well as the script details, followed by a comma, and then the sampling details as a hyper parameter underscore sampling equals to, and this object of hyper underscore params, which has all the details of type of sampling method, parameters, as well as various options. Great. And next, I'm going to specify the early termination policy as policy equals to none with a capital N. And that is because we are going to use the random forest algorithm, and it does not make sense to have any policy for that. I would always recommend it if you are using XGBooster or PyTorch or something similar. Alright, then another comma, and in the next line, let's now provide the primary metric as primary underscore metric underscore name equals to, and in quotes, accuracy. Great. And then the next parameter of the kind of goal we want for the primary metric. And because it is accuracy, we are going to set it to maximize. So that will be primary underscore metric underscore goal equals to, and a class of primary metric goal with a P, M, and G capital dot the attribute of maximize in all caps and with a Z or a Z. But we have not imported this class, so it is giving us this error. So let's just do that after this hyperdrive config as a comma. And once again, please allow me to copy and paste this class name over here. Great. And then let's provide the maximum total and maximum concurrent runs as max underscore total underscore runs equals to, and for now, let's provide the value as 20. It actually matters when you want lesser runs than the possible combinations or the sample space. In our case, we have 12 possible combinations, and it will run maximum 12 different runs. If we specify anything less than 12, let's say 5, then it will run only for 5 combinations. You can also specify the duration here instead of the number of runs. And just in case you are worried about the compute costs or want to see the results in a fixed timeline, you can specify the duration. Alright, and next, let's also specify the max underscore concurrent underscore runs equals to 2, because we have specified the maximum nodes for our cluster as 2. Great, and that completes our hyperdrive configuration. Now the next few steps are only about creating the experiment and then submitting the run. So let me create a new experiment as a new underscore experiment equals to the class of experiment, and inside the parenthesis workspace equals to WS, comma, and the name of the experiment as name equals to, and let me call it hyperdrive underscore exp001. Great. And let's also submit it as a new run. So that will be new underscore run equals to the object of new underscore experiment dot submit, and specify the config equals to the object of hyperdrive configuration, which is hyper underscore config. That's it. And finally, new underscore run dot wait underscore for underscore completion, and within the parenthesis show underscore output equals to true. Great. That's all that is required for now. And that completes our job or the configuration script for the hyperdrive experiment. That was one long lecture, and I hope you have followed me all along, and I could help you understand the steps for configuring the hyperdrive. Now, we haven't coded the training script for this hyperdrive. So before we submit it, let's do that in the next lecture, and then we will go for the submitting the run. So see you soon in the next one, and thank you so much for watching. Have fun. Welcome back. And let's now see the changes required for the training script. And I have already done those changes, and they are pretty minimal in nature. Majority of the changes are in the configuration part. So we import the run class, get the context, as well as access the workspace of this run, which is pretty straightforward, and we have seen that earlier as well. Then we get the parameters passed from the job script. So we have the number of estimators, minimum samples per leaf node, and also the input data, which has the input dataset as the named input. We then pass it and assign these arguments to these two variables. Pretty simple and nothing different than the previous training scripts. We then load the data using this input dataset and key as the raw underscore data. And the rest of the steps are pretty much the same as before. So we drop the ID column, drop all the rows with missing data, create dummy variables, create X and Y, and finally split the data into train and test. Then, compared to the previous scripts where we use the logistic regression, here I'm using the random forest classifier as RFC. And we need to use the Ensemble package to import it. I hope this is pretty much clear. You can always find this path of the import from the sklearn documentation from their website. Alright? And then, while creating the object, we now need to pass the keyword parameter values to this class. And those parameters are nothing but the arguments that we have collected and assigned to these two variables of NE and MSL. Rest of the steps are exactly same as the logistic regression. And I simply changed the object name of LR to RFC. And it actually takes care of feeding the data, predicting the values, predicting the probabilities, as well as computing the confusion matrix and the score. And finally, we are logging the score or accuracy of this training run. And now this is the most important part here. So every such script run from the hyperdrive experiment has to log the primary metric, because based on this, the hyperdrive experiment is going to decide the best run. So this is the second big change. The first was passing and collecting the hyperparameters as arguments, and the second one is logging the primary metric. Now, as long as these two are taken care of and the input dataset is properly accessed, you won't face much of an issue in hyperdrive runs. Great. And then, of course, we have this line where we complete the run, and now we are ready to run the hyperdrive experiment. So let me go to this job script, make sure the workspace is created, the input data is uploaded in the correct manner, which means the name of the dataset is correct, as well as the last column is a string and not Boolean. So if everything is done, select all and hit Ctrl+Enter to execute it. It will start displaying all the print messages that we have coded for understanding the steps, and then pretty soon it will start the hyperdrive run. But as it happens with every run, because we are provisioning the new cluster, it needs to load the environment, make the nodes ready with all the packages and installation. So it may take maybe 30 to 40 minutes to complete the entire run. So give it maybe 45 minutes to an hour and you should be fine. For now, let me end the lecture here and I will come back once it is completed. As always, it's a pleasure to teach you. Thanks for joining me here. Welcome back, and I hope you have been able to run the hyperdrive experiment. And if so, congratulations on running your first hyperdrive run. And let's now see how we can retrieve the best run, which is the one with various combinations of our hyperparameter that gives the best accuracy. And in order to show that, let me explain the hyperdrive run first. So we created this new underscore run as our run object. But this run object is not the typical run class object. And in case you wonder what I mean, well, let's go to the variable explorer and see the type for this new underscore run. Let me just adjust these frames so that you can see it properly. And as you can see, it says the type of the new underscore run is azureml.train.hyperdrive.run. This class of hyperdrive. So basically, this is an inherited class or the child class of the original run class. And to see the details of it, we can either import this class and see the documentation, or we can go to the AzureML documentation and browse it there. For import, you may have to use this path up to this run and then import the hyperdrive run class. We have seen that for many classes. So today, let's see another way of accessing the help or documentation of these classes. So go to Google and search for the Azure Machine Learning SDK for Python. Click on this link of Microsoft. So it will redirect you to the homepage of the SDK documentation. And here you can get the documentation for each and every class and function of the AzureML SDK. And it also gives some sample code as well. Then to access our hyperdrive run class, let me go to the reference. Then AzureML train core. And it is sorted alphabetically. So you will find it right here. Expand it. And then expand this train.hyperdrive link. Come down a bit and you should find our class of hyperdrive run. Click on it. And there you go. You will see the entire documentation of it, of what it contains, which is the parent class, how to construct it, or how to create an object out of it using its parameters and so on. We also have the methods associated with that class. So for this run type, some of the most important methods are this get best run by primary metric, then get children sorted by primary metric, and get metrics method. I think the name of these methods are pretty self-explanatory. And if you want, you can spend some time and read the detailed explanation as well as what parameters they expect. For now, let's go back and code some of these in Spider. So if you want to extract the best run, we can do that as best underscore run equals to this new underscore run object dot and the method of get underscore best underscore run underscore by underscore primary underscore metric with 2 parentheses. And that is one big name for a method. So this one will return the best run based on the primary metric. And if you want to print the best run ID as well as the metrics, we can simply use certain attributes of this best run object as print, and within parentheses, first the title in quote as best run ID, a colon and a comma, and then best underscore run dot ID. And next, let's print and within parentheses best underscore run dot get underscore metrics with two parentheses. All right. So we are going to extract the best run, then print its ID as well as print all the metrics associated with it. So let me simply select these lines and execute them, and then things will be absolutely clear in terms of what values will be printed here. It could take some time as it accesses multiple runs and fetches the best one, but very soon you will see the data printed over here. And there you go. This run with the run ID ending with B_7 is our best run, and it has given us the accuracy of 0.79. And because we logged only one metric, you will see just this one. Otherwise, it shows all the metrics that we have logged as part of the run.log process. Great. And next, let's go to the Azure ML Studio and see how this experiment looks there. And here under the Experiments tab, you will see this Hyperdrive EXP001 created. Click on it. And here you will see only one run, which is the master run. All our hyperparameter tuning runs will be part of this child runs of this run 1. So click on this run 1. So here it will show you the parameter sampling information first. So we have the grid sampling method and all our parameter lists right over here. Then we have the early termination policy, primary metric, and so on. Then if you come down further, you will see the run data summary. Here you will see that we specified maximum 2 concurrent runs, as well as these values as we mentioned during the configuration. Great. So let's now click on the child runs and see what we have there. So we have these 2 plots here. The first one is just the scatter plot of the run numbers and their accuracy. And it was this run 10 that gave us the highest accuracy. Then on this side, we have this parallel coordinates chart, and is also one of my favorites. Let me just maximize it a bit. And here we see various combinations of parameters and what kind of primary metric it provided. So we have this highest accuracy of 0.7961, and we can actually trace it back using the color of this line. And the way to read it is very simple. We take this line and go back to this value of 2. Then trace the same color line back to this parameter, and it gives us the value of 100. And that means the parameter value of 2 for minimum samples per leaf node and value of 100 estimators or trees in the forest gave us the best accuracy. It's an amazingly simple visualization. Similarly, you can check it for others. For now, let me just close it and come down a bit. And here we have the list of all the runs sorted as per the primary metric. So the run number 10 with this ID of B_7 is the best run, and we have all the other details right over here. We can click on this run, and once again it will present to you the typical screen with all the individual run details. If you want, you can go through it, but for now, let me just summarize what we have learned so far. As a part of this section, we have completed the important section of using Hyperdrive to tune the hyperparameters. Within that, we learned how to select a sampling method of either grid, random, or Bayesian sampling. We also learned how to define the parameter search space using their type as discrete or continuous. Then we also defined the primary metric and logged it. We then learned various early termination options and how they can be used to stop the training run. And finally, we retrieved and saw the best run using SDK as well as using the Azure ML Studio. Great! I hope you have enjoyed learning Hyperdrive as much as I enjoyed teaching it to you. Once again, thank you so much for joining me here, and have fun. Hello and welcome, and today we are going to learn another exam objective of using the Model Explainer to interpret the models. Within that, we will learn how to select different model interpreter as well as how to generate feature importance data. This is a pretty new topic, and I'm pretty sure that many of you have not seen that in many other courses. So let's first see what do we mean by model interpretation. Well, most of the time we have some input data set in the form of X or independent features and the predicted or the Y features. We then train an algorithm which gives us a trained model. Later on, if we deploy the model and provide one or more new input to it, it will start giving us the predictions. And this is simply awesome. But this trained model, in many cases, is like a black box. We don't know what was the impact of individual feature on this prediction. We may not know which features are more important than others. And even though there are some packages provided by sklearn, we still cannot figure out the impact of those features on an individual prediction. So something like why Bob's loan application was rejected. What were the features that played some role or some important role in that rejection? It is very difficult to do that. And similarly, we may not be able to interpret the features important for individual production runs. And as I mentioned, the sklearn library has these feature selection modules. But again, they are applied on the entire dataset, and we cannot extract the role played by individual features in an individual prediction. Alright, and now let's see why it is so important to interpret the model. Well, if you are a data scientist, you should be able to explain the model findings to others. Simply saying this is how it works is not enough in the real world. Also, if you know which features are playing what kind of role in the predictions, you can debug the model training and decide which additional features could be missing, or even drop some of them if they are very insignificant. That way, you can improve the existing model. Then, for the decision makers, knowing how the labels are predicted will help him or her in bringing more transparency for the end user or the customer. They can even justify the business case much more confidently. Remember, it's the organization which is spending money on these projects. And with that additional information, they may even be able to identify some more business cases or may even bring focus on certain aspects of operations, only if they understand how the predictions have been made and which features are more important. And lastly, but they are very critical role players, are the key approving authorities from legal, auditing and such. They may be able to understand the risks in implementing these models or even how these predictions can impact the humans. There could even be legal matters and they should be able to understand how and why certain decisions were taken. Only then they will be able to defend them in the court of law. I hope now you understand how important it is to interpret the models for the benefit of the entire organization. Alright? So as part of this exam objective, we will learn about some new libraries such as Azure ML Interpret, which is using different modules from the Interpret community. Then we will also learn different techniques to interpret the models based on types of algorithms. As a part of that, we will learn the local versus the global explanations and a very important concept called as Shapley values for deriving the feature importance. And by learning all of that and the final implementation using the Azure ML SDK, I'm pretty confident that you will pretty much learn everything required for this exam objective. So let's go ahead and deep dive in these topics. Thanks for watching. Welcome back. And today, as part of understanding the model explanations, we first need to understand what is known as the Shapley value. And this lecture is going to be one of those suspenseful lecture of mine where suddenly you will have a wow moment towards the end of it. And also considering the complexity of the topic, I'm going to go a bit slow here and I request you to hang in there for a few more minutes. Alright? Great. Now this Shapley value was first introduced by Lloyd Shapley in 1951. But it was only in the 21st century that people realized its full potential and he won the Nobel Prize for it in 2012. So this solution of Shapley is a concept in cooperative game theory. So when multiple players are playing a game or contributing towards an outcome, how do we know the importance of each player? How can we decide what contribution an individual player had in the game? And that is precisely what Shapley value provides us, which is the contribution as a distribution among the players. Or you can say it provides us how much cost or gain can be associated to a particular player in the game. Now to understand this concept, let's use a very simple example. Let's say three people, Alan, Bob and Cindy, want to go an event, maybe some sporting event. But they live in different suburbs and at different distances from the stadium. Cindy lives the closest, so if she decides to go to the stadium by a taxi, she will pay just $4. Bob, who is a little further away, may have to pay $6. But Alan, who is the farthest and at different end of the town, may have to pay $20. But one more interesting thing here is, Bob and Cindy have their homes on the same route that Alan will take to go to the stadium. So Bob says to them, hey, why don't we take a taxi? And then let me pick you guys up on the way to the stadium. And that basically saves them few dollars. And then they decide to share the savings. But now, the question is, how should they split up the check of $20? If they split it up equally among all the three, it's a problem. Because then Bob and Cindy are paying more than if they had to travel individually. So that's a complete no-no. And if Bob and Cindy pays the same amount as before, and Alan takes home the biggest savings, again that's not a win-win situation. The distribution of the cost or the savings should be such that all the three should be able to save some money. Only then it is a win-win for all of them. And that's where the Shapley value comes into the picture. The Shapley value wants us to create different possible combinations of these participants. Right from none of them goes to the event till all the three go together. So let's see how the cost will be for all the possible combinations. So if none of them goes, obviously the cost will be 0. And if all of them go on their own, it will cost them 20, 6 and 4 in that order. Then another possible combinations are if Alan goes with Bob or Alan goes with Cindy or Bob goes with Cindy. So that will be these three possible combinations and then their cost will be 20, 20 and 6 because they are on the same route. I hope there is no problem understanding this particular part. And here it is assumed that one who stays farther picks up the other one. And that's why the total cost won't be more than the maximum required. Then the last combination is when all the three go together. And we know that will be $20. And now we can calculate the distribution of this cost when all go together using this formula given by Lloyd Shapley. I'm sure you must be shocked to see this formula. And some of you must be thinking exactly this. But hey, don't you worry. For those who are interested in knowing the details of the formula, you can go to this link of Wikipedia or just search for the Shapley value in any of your search engines and you will get tons of articles and research papers explaining this formula. But for us, for the mere mortals, there is a website to calculate the Shapley values and let's go there and see the distribution. So here I am and by default it has the number of players as 3, which is also the case for us. If you want more, you can always change it. And the coalition here simply means the type of combination of different players. So no value inside this curly bracket simply means no combination. So the value for us for that is 0. Then 1 here means Alan, and if he goes on his own, the value is 20. Then for 2 or for Bob, it is 6, and for just 3 or when the Cindy goes on her own, the value is 4. Then if the Alan and Bob goes together, which is this 2-1 coalition, the value is 20 again. For 3 and 1, it will be 20, 3 and 2, it will be 6, and finally 20 if all of them go together. I hope you are with me. Then when I click on compute, it provides us these Shapley values for different players. So that means now Alan will share 16.33, Bob will share 2.33, and Cindy will pay just $1.33 in this total contribution of $20. And that seems pretty much fair, with everyone sharing the savings. And I hope I could make it simple enough so far. And here we took an example of these 3 people participating in an event and contributing some cost. Now imagine, instead of Alan, Bob, and Cindy, we have 3 independent features of a dataset. And while predicting the event of the predicted classes, they contribute towards the total errors or cost or gain. So they have these individual errors, and when we use them together, there is some total error in prediction as well. And we can now use the Shapley value in finding out how much each of these features contribute towards the final prediction. Great. So let's now take a real prediction example and see this hypothesis once again. So let's say we are trying to predict whether an adult earns more than 50K or not. And we are going to use these 3 features for predicting that. Then let's bring in the different combinations. And hypothetically, let's see how it impacts our prediction. So in this case, where we don't have any prediction, the chances are 50-50. Okay, so for now, I'm going to say that we will predict it as 50K. Then when we use these features individually, let's say we get the prediction of 65K for marital status, 100K for education, and 60K for the experience. Then for the pair of 2, we get a prediction of 90K for marital status and education, 63K for marital status and experience, and 98K for education and experience. And finally, when we have all the 3 features working together, we get the income value of, let's say, 88K, which is pretty close to the actual income level. I hope you are still with me. All we are doing here is taking different combinations of these features, discard the others, and then predict the income. Then if we calculate the Shapley value for these features and these combinations, you will get the Shapley value of 500 for marital status, 35.5K for the education, and 2000 for the experience level. And the sum of these is nothing but the difference between the one without any feature and the one with all the features. And based on these values, we can now determine the importance of these features. And we can clearly see here that education has the maximum impact on the prediction, and marital status has the least importance or least impact. And I hope now you understand how we can use the Shapley value for creating the feature importance for individual predictions. Great. And with that covered, let's now go ahead and see what are the different interpretability techniques using these Shapley values. As always, it's a pleasure to simplify things for you. Thanks for watching. Hello and welcome. So after understanding the Shapley values, let's now go ahead and see different interpretability techniques. But before that, let's understand what we mean by the local and the global interpretations. Global interpretability usually takes into account the feature importance on the entire dataset, whereas the local provides the feature importance for an individual prediction. So something like which features are important to get a particular accuracy or any such primary metric, that will come under the global interpretability. And something like which top features predicted that Bob has income higher than 50K is an example of local interpretability. And they can be different. So you may see the order of the top features for global slightly different than the local features. Great. Then, as a part of the interpretation of the model or feature importance, Azure uses a package called as azureml.interpret. It's also known as the interpret ML. It has its own GitHub repository, and you can also visit their website at interpret.ml. It predominantly uses the features of the open source interpret community package, mostly the stable ones. Then for Shapley additive explanations, or also known as SHARP, it uses this open source library managed by Scott from Microsoft. If you want, you can always visit their GitHub repositories and see more details of it. Great. And let's now see different techniques provided by this library. The first is the SHARP tree explainer. And as you must have guessed by the name, it is based on the Shapley values or Shapley additive explanations. We can use it for explaining the tree-based algorithms such as decision tree, random forest, and such. It is more of a model-specific technique. And what I mean by that is you cannot use it on linear or deep learning algorithms. For deep learning explanations, we have to use SHARP's deep explainer. So it supports algorithms such as those provided by TensorFlow and PyTorch. And once again, it is nothing but model-specific, means applied only on the deep learning models. For linear algorithms, we have the SHARP's linear explanations. So all these 3 explainers that we have just seen are very much model-specific. For model agnostic, or what I mean by that, is something that can be applied on any model. For such explainer, we use the SHARP's kernel explainer, or even the mimic explainer. So in case of mimic, it basically creates a surrogate model by using the different predictions. So it tries to mimic the behavior of whichever black box model we have, and then creates its own algorithm based on the predictions. And finally, we have the permutation feature importance, which many of you may be aware of. Here, we simply add or remove one feature at a time and make the predictions. Then we calculate the cost or error or gain and see what has been the impact of the change by means of bringing that or bringing in that feature or removing that feature. If the impact is bigger, that means the feature is more important. All right. And then, apart from these 6 explainers, Azure ML also makes use of the tabular explainer for the tabular data. It is also a sharp-based explainer, and depending upon the type of model, it makes use of either a tree explainer for tree-based models, or a deep explainer for deep learning, linear explainer for linear models, and finally the kernel explainer for all the other models. Great. And I hope that gives you enough understanding of different techniques and where it is used. Now, before we complete, let me summarize the benefits of using the Azure ML Interpret package, or I would say the benefits of interpretability in general. Now, using this package or using the interpretability, we can explain the entire model behavior as well as the individual predictions on local machines as well as on Azure. It also enables the interpretability of the engineered features. So you may create different features from the existing one or even modify the current ones, which is loosely speaking is nothing but the feature engineering. With interpretability, we will be able to provide the explanation of the models for all those features. You can even use the visualization dashboard and create various charts such as dependency or partial dependency chart for model explanations using this package. And finally, you can even apply it on the production and start explaining why a particular record has been predicted as positive or negative. It's a huge boost in terms of transparency, because now you can tell the management as well as the customer why your algorithm predicted a particular outcome for an individual record than simply telling them this is what algorithm predicts based on this data. Great. And with that covered, when we implement the explanations using Python in the next few lectures, we will cover everything related to this exam objective. So see you soon in the next one and have a great time. Thanks for watching. Welcome back. And now that we understand what are Shapley values, the difference between global and local explanations, as well as various interpretability techniques and the tabular explainer, let's now go ahead and implement them. For this, I'm going to use a smaller dataset or a subset of the original adult income dataset. In this one, I'm simply using the age, WC for working class, level of education, marital status, race, gender, and the working hours per week. Based on these, our model is going to predict whether the income of this individual is greater than 50K per annum or not. Alright? And now, before we start working or start coding our experiment in Python, you should install these two packages of Azure ML Explain Model and Azure ML Interpret in your local environment. And I'm pretty sure you now know pip install to install any package. So let's go to the spider and see what are we going to do with the adult income dataset as well as these packages. I have already copied and pasted this Python code here. It's pretty straightforward and you should not face any issue in understanding these steps. So I have changed the file name to this truncated one of the adult income file. This dataset is very much clean and that's why I haven't done any data cleaning as such. We straight away do the dummy variable creation, then create x and y variables, and then split them into train and test. For creating the model, we are going to use the random forest classifier. We create the object of it and then train the algorithm using this fit method. And here you may see some slight change. And instead of simply fitting it to the object, I'm also collecting the output object in this trained_model variable. And you will very soon understand why I did that. After that, we have the usual steps of testing the model by using the test dataset and getting the confusion matrix and the score. Great. If you want, you can go ahead and execute this script and create your trained model. And in the next lecture, let's go ahead and code for the model explainers. Before starting the next one, I suggest you first install the two packages of Azure ML Interpret and Azure ML Explain Model. Thanks for watching. Welcome back. And now let's start coding for the model explainer. Here, I'm going to use the sharp-based tabular explainer. And first, we need to import it as from interpret.ext.blackbox import the class of tabular explainer with T and E capital. Okay. Then let's create an explainer object from this class and let me call it tab_explainer equals to the class of tabular explainer with two parentheses. Now the constructor of this class requires a few parameters and the first one is the trained model that we have created. So inside the parentheses provide trained_model comma and next it needs the training data which we have in x_train, another comma, and now the next two parameters are about the features and the class names. So that will be features equals to, and let me provide that using the same name variables as features, a comma, and then classes equals to classes. And it is bound to give us this error that features and classes are not defined. So this features parameter expects a list of independent features for which we want to generate the feature importance values. And this classes expects the list of predicted classes. So just before this tab explainer, let's define the classes as classes equals to 2 square brackets. And here we need to provide the class names of greater than 50K or not and greater than 50K. But we cannot provide these values just like that. Let me first open the data in Y. And here we will have only one column of income class greater than 50K. So a value of 0 here means it is not greater than 50K and 1 means the opposite. And we need to provide the list of classes in the same order, which means the 0 will come before the class value of 1. So then in this list of classes, let's provide in quotes not greater than 50K as the first one, comma, and in another quotes greater than 50k. I hope this is clear. Next, we need to provide the names of independent features in a list called features. Now, this could be a huge list because of this dummy variable creation. So instead of searching for them and providing them in square bracket with so many names, we can use the column attribute of the X data frame and then use the list function to convert that into a list. Let me just show that as features equals to the function of list and inside the parenthesis X dot columns. Great. So with this class imported and with this object definition, the constructor, all the parameters defined, we can now create the object here. And now let's code for getting the global explanations from this explainer object. For that, we need to use a method of this object called explain global. So that will be tab underscore explainer dot the method of explain underscore global. And within the parentheses, we need to provide the training data as X underscore train. So this method will first create different combinations of the features, and then based on the trained model and the training data, it will create the feature importance. And this is going to return an object with explanations. So let's collect that in global underscore explanation equals to this entire statement. And now let me select these lines and run them so that we have the global explanations created over here. It is going to take some time as it creates multiple combinations of these features and then calculate their importances. So I'm going to pause the video here and come back once it is done. It has finished running for me. Great. Then next step is to get the feature importance data from this global explanations object. And let me collect that as global underscore fi for feature importance equals to this object of global underscore explanation dot get underscore feature underscore importance underscore dict for dictionary with 2 parentheses. So this method will simply create a dictionary with the feature names as the key and their importances as the value for that key. There are multiple methods associated with this object and I'm simply using this particular one. So let me just show you all the methods, and for that let me open the global underscore explanation object. Scroll down a bit and you will see all of these get methods for getting the global values, either ranked by their names or values and so on. Their names, as you can see, are pretty self-explanatory. But if you want to know them in detail, you can simply click on them and have a look at the explanations to understand what they do. Great. Let me close this for now, and we are now ready to run these explanations. So select all the lines and hit Ctrl+Enter to execute them. It is going to take some time because first it's the random forest algorithm, and then secondly it is because of these various Shapley combinations that it will build. So let me pause the video, and when we come back I will explain various features and their importances. It has finished running for me, and now let me open the global FI dictionary and see what we have got there. And here we have this dictionary with 18 keys or the 18 features and their importances as the values. And if you click on the values, you will realize that race other has the lowest feature importance. And then the education preschool appears to be the highest. But no, hang on a second. It's not actually the case because this education preschool is with a power of -5. And that's why it would be the lowest actually. And the marital underscore status of married appears to have the highest impact in predicting whether the individual will earn more than 50k or not. Then comes the age, number of hours per week that the person has worked, education of high school grad, and so on. And now you can explain what are the top most important and the least important features which are impacting our predictions. If you want, you can print them, log them as AzureML metrics, explain them to others, or do whatever you want to do with it. Great. And if you have been doing it along with me, congratulations on learning how to derive the global feature importances using the interpret package. In the next lecture, let's see how to get the local feature importance using another method of this tabular explainer. As always, thanks for watching.